before we move on to cryptography. So the next project, as I mentioned, is on web security attacks, and so you will be implementing the kinds of attacks that we just talked about on a server running in a virtual machine, so you don't have to attack real websites, because people get annoyed when you do that. So we're now going to start talking about cryptography. A quick question, how many people have taken a cryptography class before? So about half the people. So this is going to be pretty boring for you when we talk about cryptography. This is sort of baby cryptography. I'm not a cryptographer. I'm a security person. So it's sort of more applied and what are the things that we care about. But it's going to be, a lot of things you have seen in much, much, much more detail. But if you haven't seen cryptography, my goal is to sort of communicate enough of what you need to know to sort of understand sort of the role that it plays and what the issues are in using cryptography correctly. So one thing to know is that cryptography deals with secrets. So the key idea with cryptography in a way is that if you have something secret, then you can communicate information that nobody else can modify or can see. It turns out that developers don't always know what secret means. So if you go and look at GitHub, you can find a lot of people who embedded like their AWS developer key in their code as, like AWS key equals in some string and then put it on GitHub in a public repository, and you can just find lots of secret keys that get you access to all kinds of things by scanning GitHub. People also have done this in things like Docker repository or virtual machine images for AWS, where people just put their key in a file or in a script or an environment variable somewhere that is then put in a publicly visible place. So number one rule of cryptography, keep your secret secret, or else all the cryptography is useless. So what we're going to do is talk about kind of the basic goals of cryptography. We're going to do a little bit of sort of how TLS, which is HTTPS, or the protocol used for securing the web, works. And it's not going to make a lot of sense at this point because we haven't learned any of the underlying techniques, but you'll get a flavor of how we combine these things. We'll talk a little bit about provable security, like what does it mean to prove that something is secure? And then we'll talk about one-time pads in here. We probably won't get to block ciphers today. We might not get to much of this today. Okay, so cryptography is really sort of the art of hidden writing, and it deals with building security protocols where you can communicate or store data. And the idea is we are dealing with an active adversary. So we have somebody who is trying to see what we're doing and can actively, they can either passively look at the information we're communicating, they can actively inject new messages. They have access to big computers that can execute very quickly, trillions of instructions per second. And we have to think about what can we do to communicate in the presence of such an adversary. And there's a mix of mathematics, because at the very bottom of this is figuring out what are sort of math problems that can resist trillions of operations per second and can't be solved quickly. We have engineering, which is how do we take these math primitives and sort of combine them into higher level operations that programmers can use. And there's computer science, which says how do we sort of build strong protocols that sort of respond to adversaries generating inputs, to messages being dropped, to actually always have secure, correct behavior. So here's sort of an example of how you might use cryptography on the internet. So you don't want to reveal data too early. Suppose you have stolen some US diplomatic cable information and you want to make it public. You'd like to send it to Julian Assange by sending it across the internet, but you want to store it in some way that you can get it to quickly later. So you don't want to store it, for example, in some server in a silo in Nebraska that isn't on the internet to keep it secure, because that would make it hard to get to. You'd like to store it in some very public place in a way, but encrypted so it can't be seen. So the way you can do this is you can take the data you have, you encrypt the file so it looks like garbage to everyone else. All you have to do now is hide the key itself. The contents of that file can be distributed to all newspapers anywhere you want, because the idea is you shouldn't be able to get any information about the contents of that file without the secret key. All you need to do is store that secret key. Now I will note that making sure you can get to the key is important. Some of you may have heard about a Bitcoin company in Canada where the person was trying to be very secure, so they stored $140 million in Bitcoin in an offline server that wasn't on the internet, so it couldn't be attacked. It was encrypted with a secret key. Unfortunately, only the founder of the company knew the secret key, and then he died without telling anybody. So the company lost $140 million in Bitcoin, and nobody can get it back because the encryption was actually pretty secure. I will say, though, I would think that if there was ever an incentive to try to break encryption, the ability to find $140 million in treasure, is a strong incentive to try to break that encryption. So storing your keys securely and in a way you can get to them is important. Okay, so that was for storing data. Another thing you might want to do is secure internet communications. So we want to communicate across the internet, and there's lots of things out there on the internet we don't trust. So between my computer and the internet, there's a wireless network. Any of you in here could be watching all the bits on the wireless network that go by and seeing my traffic. So I'm worried about confidentiality. You might see the information when I'm typing about the students in my classroom. I don't actually do anything, don't worry. I might worry about integrity. Again, can you change the information that's going by? And we worry about authenticity. When I connect to a bank, do I know it's the real bank that I'm connecting to before I provide my information? Does the bank know that it's actually me before it allows me to transfer money? Sometimes we want to provide anonymity, which is the opposite of authenticity. We want to make sure that a website cannot know who you are, so that you can sort of deny everybody in the world can plausibly deny that they sent a message. Sometimes we use what's called steganography. So steganography is when you have some public information and you sort of hide a secret in it. So for example, people have taken JPEG images, and by sort of changing some of the pixels in a way that's not visible, you can embed information into a JPEG. And if you just look at the picture, you don't see it, but if you have the right program, you can extract that information that says, here's the secret image. And we're not going to really deal with steganography. So to solve this problem, there's a bunch of protocols that have been developed, and a protocol is really just a set of rules that says, here is how you format messages, here is how you encrypt things, here's what you do to encrypt things, here is what you do with keys, and if everybody follows these rules, then you can communicate securely. So the major ones that are used in the internet are TLS, which is used for websites, SSH, which is used for remote login, IPsec, which is used for sort of connecting two networks together when you really want to sort of make it look like one bigger network, but you have some insecure link in the middle. So in this example, we might want to use, when you're sending traffic, it's going to go to some local switch. So all the wireless traffic in here goes to some wireless base station. That will connect to some other switch, your internet service provider, which will then cross that local network. The internet service provider will send it to a backbone network or two that will take it across the country, where it will leave that backbone and go to some other service network at the other side, where it then exits that and actually goes to the network of the company or person you're talking to, and then finally into their machine. So we can see that there's like lots of untrusted stuff in the middle here who could be looking at our traffic and could be manipulating it. Although the easiest place to find somebody's traffic is really at the end, because then you're in the same room with them, in the same building, you know who they are, there's not that much traffic. By the time you get to the middle of the internet, there's terabytes of traffic flowing by, so it's very hard to find the information you're looking for. So another thing we might want to do with cryptography is just encrypt all our data all the time. So, most phones do this at this point. For example, the university requires that if I store student records on my laptop or my computer, the data has to be encrypted all the time, so that if somebody steals my laptop, they can't get access to that encrypted data. You can either do this for the whole drive, which says we're going to encrypt everything on the drive. This has the upside that you don't have to choose what to secure, but the downside that it makes everything slower. You can also choose, in some cases, predict which files you want to encrypt. If there's specific files that are important and other files that aren't. So like I might choose to encrypt my student grade data, but not choose to encrypt the MP3 or the movies that I have on here for when I travel. And there's a whole bunch of things that do this. This is pretty easily available on most operating systems now. And again, it's cryptography, and the idea is that there's, without that access to that secret key, whatever is encrypted shouldn't be, shouldn't provide any information to users. So the interesting thing about cryptography is that we have this incredibly powerful tool, and yet it's incredibly hard to use. And the reason is that there's lots of subtle things that can make cryptography bad. So for an example, when an early Netscape web server was doing SSL, or TLS, which is the secure web protocol, but part of that had to pick secret keys for encrypting things. The way they picked the secret key was they called the random number generator in Unix. The Unix random number generator needs a seed that says, where do we sort of start getting random numbers from? And to get a random seed, they just called time, get time, which returned a 32-bit time. And they used that to start the random number generator that picked the secret key. So can you think about why this might not be super secure?
As far as I'm aware of the RAND function, the security system is not actually very secure.
Right, so the RAND function itself is really just this thing that does modular arithmetic, so it doesn't produce really random numbers. Other problems with this? Yes? So one problem is the time granularity is pretty low, so it's a 32-bit value, which means even if you think you're encrypting with a 128-bit key, which we'll see later, your randomness is just 32 bits, and so it's, you can't actually use, you're not going to use all 120 bits that are random. You're only going to have 32 random bits that you in some way repeat multiple times. And so all you have to do is guess that time value, and then you can predict what the key will be. Other problems with this approach?
If someone finds out the time that you send something, you just reverse engineer it.
Right, so time is something that actually most people already know. It's not a secret. So if you use time as your secret information, it's like the worst secret because everybody in the world knows what the time is. Right, the time could be a little bit different, like the milliseconds field might be different when you do something, but people sort of know seconds or hours. And so most of the information that you're using to generate your key is information that's publicly available. And so it's actually relatively easy to just compute all the keys that could be used, all the possible random number seeds, and use that to compute all the possible keys, and then decrypt your traffic. And so the point is you have to sort of think through every step of the protocol of how you use this and design it securely. And the other problem is even the low-level primitives we use for encryption get broken sometimes. That there's not a real science of building a system that can never be broken. It's like, they try to build things that we don't know how to break, and we hope they're good enough for a while. So there's a basic design principle here, which we covered a little bit when we talked about secure systems in the beginning. This is August Kirchhoff's principle. He has 6 principles. This is the second one, the only one people care about. And the gist of it is that you should design a security mechanism, an encryption mechanism, where the mechanism itself is publicly known, and the only thing that secures it is knowledge of that secret key. That you should not rely on the secrecy of the actual mechanism involved. And the idea is that you can't necessarily control the secrecy of the algorithm because you have to distribute that where whoever is using this mechanism has to have that in it. So for example, if you're a cell phone company and wanted to have a secret mechanism for encrypting data, we've got 1 billion people with that mechanism in their pocket, which makes it very hard to secure. If an attacker breaks into your website and they find the mechanism in your source code repository, you're out of luck. And changing your mechanism is very hard, whereas changing your secret key is relatively easy. It also says that this might encourage you to sort of make your mechanism public, which means that a lot of people can see it, look for problems in it, debug it for you, help you fix it, whereas if the mechanism is secret, then there might be lots of problems in it that you're not aware of that attackers do find out when they find the mechanism. So this is really sort of philosophy which is pretty aggressively followed at this point. And in general, if you ever read about a mechanism where they won't tell you how it works, you should basically believe that it's totally useless and very easily broken, because that is pretty much always the case. Okay, so we're going to talk first about a bunch of primitives, which are sort of the basic mechanisms of encryption. We're going to go through what they're used, what they do, how they work, not how you implement them, but sort of what these primitives are good for. And then we'll talk later about how you actually implement some of these things. So there's encryption, which provides confidentiality. This takes your good data and scrambles it. And there's 2 different kinds we'll cover, symmetric and asymmetric. There's a message authentication code, which is a way that you can take a message and append some extra data such that if either the message is modified or the data is modified, you can find a discrepancy. And you can also tell who generated the message. So think of this as like a secure checksum. There's a digital signature, which is another form of this, but it's meant to be public, so it's an asymmetric mechanism where I can digitally sign something, then everybody in the room can verify it. So this is a particular form of a message authentication code. And then key exchange is the idea of if we want to have a secret key to communicate, where I can encrypt data, you can decrypt it, we have to somehow create that key and we have to start sharing it. So one way is for me to walk up and hand you a piece of paper with a key on it. That doesn't work for the internet. So we need ways that you can create a key to encrypt data for your web server to see. So there's key exchange mechanisms that provide this. So in talking about cryptography, there's some historic conventions that I don't understand where they come from. They're somewhat, I would say, Eurocentric in terms of always dealing with white European people as the characters in the story. So we always have Alice and Bob. These are the two people who are communicating, who want to communicate. These are sort of the protagonists in our story. It's Alice wants to send money to Bob. Alice wants to send email to Bob. Alice wants to send money to do all kinds of things. And so they're the ones that are trying to communicate somehow in both directions. We then have Eve. Eve is an eavesdropper. So Eve can actually read all the messages that Alice and Bob send back and forth. But that's all Eve can do. So when we think about Eve, we're thinking about an attacker who can see messages, and we're saying just from seeing messages, what can you do? So if you think about in the military, you're working signals intelligence, you're listening to encrypted radio signals, and you want to decrypt it and see what the enemy is doing. In this case, you are Eve. So this is a passive adversary. We then have Mallory, and I don't know why all the evil people are women in this story, but Mallory is more malicious, and Mallory can actually be an active adversary and inject messages into the network. So Mallory may record messages at one point and replay them later. Mallory may inject requests to sort of send specific data to a web server and see what it responds. Mallory can sort of, Mallory doesn't know what the secret keys are, but can do anything else that she wants. So the nice thing is this gives us name. If you hear Alice and Bob, you think nice, friendly people. They're likely victims in the story. If you hear Eve, Eve is just listening in on the thing. If you're Mallory, you know there's going to be some action where Mallory's going to actually try to attack people. Okay, so we're going to start off with symmetric encryption. This is sort of the most basic mechanism most people are familiar with. The idea is we're going to have some key, K, that both Alice and Bob have at the start of the story. So they both have this secret information. Hopefully they're the only two people who have the secret information. Alice is then going to take some message, M, and going to encrypt it. The M is called the plain text because it's plain, anybody can see it. Anybody who has it can read it. It's going to be encrypted with the key. This will produce a ciphertext C. Eve can see this ciphertext because it's going across a public network, and then Bob will use the same key to decrypt it. So the interesting thing to know here is that Alice and Bob are using the same key, and it has to be secret because anybody who has that key can decrypt the secret messages. Okay? So what would happen in this system if Mallory, for example, recorded C, and then later on sent C to Bob? Right, that's fine. Bob would see that message C. Bob can decrypt that message C. And hopefully Bob would know that it's been replayed through some other mechanism, but so far there's no way to stop that. Similarly, Mallory could replay the message to Alice. Alice can also decrypt this message because she has the key. So anything that Alice produces, she can decrypt and Bob can decrypt. Any questions on symmetric? This is also called, by the way, secret key encryption because both the key here has to be kept secret. But we'll call it symmetric because both sides do the same thing. They use the same key. So next up, as you might guess, we have asymmetric encryption. So here, Alice and Bob have a pair of keys, what's called a private key, a public key, and a secret key. And the secret key, the idea is that they're inverses of each other. If you encrypt something in the public key, you can decrypt it with the secret key and vice versa. The other thing we assume now is that Alice and Bob know each other's public keys, but only Alice and Bob know their secret keys. So you can see already this is a better mechanism because the only thing the things that are secret to one person. You might have heard, secrets are not secrets when you tell them to someone else. So Alice and Bob don't have to have a shared secret anymore, which they did in the other mechanism. So this makes it potentially more secure. So here, when Alice wants to encrypt a message, Alice will encrypt it with her private key PKA. Sorry, I didn't read my own message. With Bob's public key PKB. So she's sending something to Bob. So when she encrypts with public key B, which she knows, this will produce a ciphertext. Eve can see this. When Bob can decrypt it with his secret key. So the idea is you encrypt with a public key, you can decrypt with a secret key, and then Bob can see what the message was. Eve cannot see what the message was. So what if Mallory generated a message and encrypted it with PKB? What would happen? That's fine because PKB is public. It's okay for Mallory to know it. Bob can decrypt the message because Bob knows the secret key, but Alice cannot decrypt that message. Eve can't decrypt the message. Mallory can't decrypt the message she just created. So again, this means that Bob had better know where messages are coming from if we want to make sure he doesn't do the wrong thing. Okay, so we'll look next at a message authentication code. So message authentication code is to make sure a message hasn't been modified. So we are going to take a message, run it through this message authentication code, which has a key in it. It's going to produce some output, a tag output. We're also going to send the message potentially in plain text unencrypted on the network. So we send both of these. Mallory may try to change this message if she wants to. When Bob gets the message, the goal that Bob wants is to verify that the message was produced by Alice and not modified. And this case is using secret key, symmetric key encryption, so Alice and Bob have the same key. And so you can think about, for example, creating a checksum of the message and then encrypting the checksum with the key as one way of doing this. Another way you might do it is to create the checksum of the data and then append the key and checksum the key into that checksum and send that combined checksum, which you can only do if you have the right key. So the key thing here is that if you inject a message, so if Mallory tries to inject a message, Mallory can't inject a new message because Mallory can't generate the right tag. And if Mallory modifies the message or the tag, then Bob can detect it because they won't match anymore. What I showed was a symmetric version, but when we talk about this MAC here, you could use a asymmetric version, asymmetric encryption instead, and we'll sort of show that in the next example. So any questions on MACs? Okay, so finally next we have digital signatures. So the job of the digital signature is that Alice wants to produce something and she wants to sign it so so that everybody knows that it came from Alice. So for example, this is a lot like signing your name on a piece of check. So people know that the check came from you. Signing a contract, people know you agreed to it. We want to have some way of signing something so somebody can look at it and say, Alice produced this because of something on there. So in this case, we'll take this message and we will sign it, which means that we will do something like encrypt it with the secret key of A to create a signed message, a signature. And then we can put this on the message. So this might be just encrypting the whole message. It might be creating a checksum and then encrypting the checksum with Alice's secret key. And the thing to note is, who could produce this signature? You have to have the secret key. Only Alice has the secret key. So only Alice can create a valid signature. Here we worry about Mallory modifying the message or the signature, and Bob will verify it. So Bob will take the public key, can create the checksum of the message, use the public key to decrypt the signature, and see if the checksum matches. So anybody can verify a signature because you need a public key, but only the person sending it can produce the can produce the correct signature. So this will tell Bob, is this valid or invalid? Any questions on signatures? Yes.
Does something similar happen for certification or for certs for websites?
Yes, something definitely. So we'll talk about certificates or websites later on, but the same mechanism is used here. Absolutely. So the final thing is key exchange. Oh, yes. Right. Wait, when do you do what? So a message authentication code doesn't encrypt anything. A digital signature doesn't encrypt the content. In both of them, you're taking the clear text content, you produce some checksum over the clear text, and then you can encrypt that checksum only. And then what you communicate is the clear text and the encrypted checksum. Yeah. So there is a terminology MAC that encrypts. So if you want to encrypt the message, also you can either compute a MAC or digital signature of encrypted data or unencrypted data, but they're separate things. So you can choose: do you want to encrypt first? If you want encrypted data, you can encrypt it and then you can compute the MAC, or you can compute the MAC and then encrypt the data after you compute the MAC. But you have a choice as a designer, the order. The MAC just says whatever data you get, we're going to produce this method authentication code. But the data itself can be anything encrypted or unencrypted. The checksum calculation has whatever key you pass into it, and you could use a public key if you wanted to, but it wouldn't be very meaningful because anybody could do that. So you typically want to do that with something secret. So we'll wrap up with key exchange. I apologize, I'm running over a little bit. Basically, the idea here is we want to create a shared secret symmetric key between Alice and Bob. We want to do this while Eve is watching all the messages, though. So we want to exchange some set of messages that Eve can see, and we want to end up with a key that Alice and Bob both know, but that Eve can't see. So we will stop here because we're out of time, and we will pick up on encryption more on Thursday. There's some readings on the web page to kind of help you understand the things we'll be talking about.